Hello, Physics 11 students. You guys are doing well. I'm looking outside here. My son's out working in the garden, and I'm thinking that it's not too bad a day out there. And here I am inside with you doing physics. All right. So I was going to go over the questions I assigned, questions 10 to 20, the 6.8 review. So there's going to be like a quiz test next week. I think I said Tuesday, but I'm not sure. I was going to be sending out a review on Monday is the way I was thinking. All right, let's take a look. Question number 10, a Saturn V rocket. These were the big rockets. These are the rockets that sent men to the moon, and they were huge. I was reading a story where the newscasters would be following the program, the system, and they were set up for the first time with the Saturn V rocket, and they had their little tents up where they were protecting from the sun and everything like that. And they were used to smaller rockets going up, and there would be a roar and be kind of fun and exciting. Well, when the Saturn V rocket happens, now that would be several kilometers, a couple of kilometers away for safety's sake, and the rocket starts going up before you hear it because the sound takes time. And the guys were in their booths, and all of a sudden, they saw the rocket going up, and then the blast hit them, and it just blew their tents over, just with the incredible blast of air that came from the rocket. So really quite amazing. Anyways, so here I was a space geek. You know me. I even applied for the space program. So the Saturn V rocket with a mass of 2.92 times 10 to the 6 kilograms has an engine thrust of 3.3, let's get rid of that, 4 times 10 to the 7 newtons. First of all, we want to know what the force of gravity is. Well, force of gravity is equal to mg, gravitational field strength. So that's 2.92 times 10 to the 6 kilograms times our 9.8 newtons per kilogram. And so that works out to be 2.86 times 10 to the 7 newtons. That's how much this rocket weighed sitting on the launch pad. Then we want to know what the net force is, so here we've got a rocket. Well, you can put a point on the top. Here's our rocket. So we've got the force of gravity pulling it down. The rocket engine blasts, and so there's rocket smoke and stuff that's being pushed out the bottom. So this is the initial direction, but there's a reaction force which goes in that direction. So when we talk about a rocket, we've got the force of gravity going down. The rocket engine throws material downwards so that we have a thrust going upwards. It's Newton's third law. That is the only reason why rockets work, is because Newton had a third law. If he'd stopped at number 2, no rockets. That would be it. All right, so we need the net force. And so the net force, well, that's going to be equal to the force of our thrust minus our force of gravity. So that's going to be equal to our 3.34 times 10 to the 7th newtons minus our 2.86 times 10 to the 7 newtons. And so we have a thrust of 4.78 times 10 to the 6 newtons. So that's the net force. That's the amount of force that's pushing the rocket upwards. All right, so then we want to know, well, what's the acceleration? Well, remember, Fnet is equal to ma. These are vectors, and so we're going to take our net force. Well, you can say our acceleration will be equal to our net force divided by the mass of the rocket. So our net force is 4.78 times 10 to the 6 newtons, and our mass is 2.92 times 10 to the 6 kilograms. And so our acceleration is 1.64 meters per second squared. So, a person, no, so that's, when these things took off, it seemed like they were going so slow. Question D says, all right, so as the rocket travels upwards, the engine thrust remains constant, but the mass of the rocket decreases. Why? Well, the rocket is mostly fuel. And when you're burning the fuel, you're getting hot gases. They're being thrown out the bottom. And those hot gases represent mass. So you've got our rocket, and the rocket engine is throwing hot gases down this direction. And so as it throws them that way, then we have this thrust going up. Haven't done for a few years, but used to create bottle rockets, water bottle rockets. And you would take in essence, your bottle, you would put some water into it, and then you would air pressure. You take a bicycle pump and you pressurize it. Then when you pulled the release, the water would get thrown down this direction, and that would push the rocket up in that direction. The water's fairly heavy, so when throwing it down that way, you'd get quite a good height going up the other way, but it would be lighter. The other way of thinking about this, if you're driving your car, well, you go to a gas station and you need to fill up with gas. When is it heaviest? Well, you're putting fluid into it. When it's full of gas, it's going to be heavy. When it's empty, when you're low on gas, it's light. Now, we're not throwing the gasoline outwards, but we're burning it, producing gases, and those gases come out our exhaust. And so this is mass that we are losing from our car. All right, so the next one is the acceleration more, less, or the same. Well, Fnet is equal to ma. So our acceleration is equal to our net force over our m. So as as m decreases, acceleration increases. So as the mass is being lost from the rocket is going to be going faster and faster and faster, or accelerating faster and faster and faster. And yes, there's a message for me. And so that's just the way it's going to work. All right, number 11. We have a 13,140 kilogram V2 rocket. Now, the V2 rocket, this is a Second World War rocket that was used for putting bombs from Germany into England and stuff like that. And it was being designed by a fellow named von Braun, German scientist. Well, after the war, he was taken to the U.S. where he created the Saturn V rocket. Kind of interesting. Anyways, it produces 2.63 times 10 to the fifth newtons thrust. And what is the acceleration? So you've got a rocket and stabilizers, and it's throwing. So you're going to have force of gravity. You're going to have net force, force of thrust. going upwards. All right, calculate the initial acceleration. So we're going to have our Fnet is equal to ma. So our Fnet is, well, first of all, we need the force of gravity. Force of gravity, mg, so that's equal to 13140 times our 9.8. And that works out to be 1.29 times 10 to the 5th newtons. So our net force, so if we're taking upwards, in essence, to be positive, so we're going to have 2.63 times 10 to the 5th newtons minus a 1.29 times 10 to the 5th newtons. And that's going to equal our mass, which is 13140 times our acceleration. So we're going to subtract these, divide by that, and our acceleration comes out to be 10.2 meters per second squared. 10.2 meters per second squared. Now, not in this case, but I just want to present it here. So this thing is taking a 10.2. If you take 10.2, if, this is a sidebar, if you take your 10.2 and divide that by our 9.8 meters per second squared, we get a value of 1.04. So it's accelerating at 1.04 times the gravitational pull. And that is sometimes expressed as G's. We were pulling G's. We were accelerating at 1.04 times the normal force of gravity. So, you know, if you weighed 98 if you have a force of gravity of 98 or 100 newtons pulling you down, if you're in here, you're going to be experiencing an acceleration. Well, you're going to feel twice your weight. You're going to feel, because you'd be feeling the acceleration and you'd be feeling the force of gravity, so you'd be feeling twice your weight. If you were in space, then you'd just be feeling this force of gravity. So anyways, the point is that sometimes questions are answered in terms of G's, and it's just a multiple of that. All right, so the next part of this question states, what's the rocket's acceleration near burnout? The net force remains the same, but the mass is now less. So what we need to do is we first of all need to calculate the new force of gravity. Actually, I made this mistake. I didn't do this the first time when I was going through the questions. And so I was coming up with this wrong answer. And I was wondering, well, why? And then I realized, oh yeah, missed this. So the mass of the rocket is now 4170 times 9.8. So that's equal to 4.09 times 10 to the 4 newtons. And so we're going to have our net force, so F net is equal to ma. So we'll still have our 2.63 times 10 to the 5th newtons, minus now 4.09 times 10 to the 4 newtons. And that's going to equal our mass. Well, our mass is now 4170 times A. And when we do that, then we get A is equal to 53.3 meters per second squared. So as we lose mass and the mass decreases and the force of the thrust remains the same, our acceleration has now increased greatly. So if we take our 53.3, divide that by 9.8, we're looking at 5.4 Gs. for that. All right. We already did this. Done. All right, here we have a situation where we've got a stone and it's in the water and it's sinking downwards. And it's sinking downwards at 5 meters per second. And we want to know what's the force going up. So we're going to have a force of gravity going down, and then we're going to have the force of water that's going up. All right, so V is equal to 5.0 meters per second. So what is our A equal to? Well, it's uniform motion, which means A is equal to 0 meters per second squared. So our Fnet is equal to ma is equal to our mass times 0, which is equal to 0. So our Fnet is equal to 0. Well, what forces do we have? Let's say downwards is positive. So we have our force of gravity plus a negative force of water is equal to 0. So our force of gravity is equal to our force of water, and that's equal to 5 times our 9.8, and that's equal to 49 newtons. So these forces, one going up, down, one going up, they're going to have to be equal to each other. All right, what about the fan on the sailboat? Okay, so here we have our sailboat, and we've got our sails here, and we've got our boom here, and we've got George who sets up the fan, and the fan is blowing air in this direction. That's supposed to be him looking smart. And there's the cord going off. All right, so why shouldn't this work? Well, as the fan is blowing air in this way, there's a force. And so if that air was moving this way and was hitting the sails, then you're going to get so the wind pushes the boat pushes so we're going to get a motion of the boat going in this direction. But at the same time, what we have is Newton's third law says there's a reaction force that's going backwards. And these two forces have to be equal to each other. So there is no net force. Our net force is still going to be equal to 0. No motion. Yeah, I mean, what you can do is reach down and, pull on your shirt and lift yourself up by your shirt. How hard do you have to pull to lift yourself up by your shirt? You can't. Or sit in a chair and grab the arms of the chair and try and lift yourself up by pulling up on the chair. You can't, because as you're pulling up on the chair, you're pushing yourself down into the chair. There is no net force upward. Just doesn't work. All right, 14. What is the change in V with a net force of 2 times 10 to the 4? I can't see this. There's a little thing missing, so there's 4 should be up there. On a 2,000 kilogram dragster, and it was operating for 6 seconds. All right, so F net equals 2.0 times 10 to the 4th newtons. Our mass is equal to 2,000 kilograms. Our time is equal to 6.0 seconds. What we need is our acceleration, and that's going to get from F net is equal to ma. So we have 2.0 times 10 to the 4 newtons is equal to 2,000 kilograms times our acceleration, and our acceleration then comes out to be 10 meters per second squared. All right, so then it becomes a kinematic question. So we have our B naught is equal to 0. And what we're looking for is our V. And our time is those are 6 seconds. So we can go V is equal to B naught plus a T. V is equal to 0 plus 10 times our 6.0 seconds. So V is equal to 60 meters per second. Well, if we're talking about change in velocity, that's equal to V minus our B naught. So that's equal to 60 minus 0. So that's equal to 60 meters per second. All works out. All right. So what is the net force on a 4,000 kilogram truck going from 22 meters per second to 8 meters per second in 3.50 seconds? Well, what we need to do, so Fnet is equal to mass times the acceleration. So to calculate our Fnet, we know what our force is. Mass is. That's 4,000 kilograms. We need to know what A is in order to calculate this. So we're going to use our V naught is equal to 22.0 meters per second. Our V is equal to 8.0 meters per second. Our time is equal to 3.5 seconds. And we want to know what our acceleration is. So we'll use V is equal to V naught plus a T. And so we'll have 8 is equal to 22 plus A times our 3.5 seconds. So we're going to have 8 minus 22, and that's equal to negative 14, is equal to 3.5 times A. So our A is equal to negative 14 divided by 3.5, and that comes out to be negative 4.0 meters per second squared. So there's our acceleration. We want to know what the net force is. So Fnet is equal to ma. There's our net force. Our mass is 4,000 times our negative 4 meters per second squared. So that's equal to negative 16,000 newtons. Now, I'm not giving a direction. There's no compass. I'm not saying north and south, which they do in the textbook, but leaving in the negative sign that tells us in the opposite direction. How long for a 50 kilogram rider on a 10 kilogram bike to accelerate from 0 to 4 if Fnet is so on? All right, so when we're talking about how long, what we have is V naught is 0. We have a B that is 4.0 meters per second. T is what we're looking for, so we need an A. And to get that, we're going to have to use our Fnet is equal to ma. Our net force, so that's 48, is equal to our mass. Well, our mass, is it 50, is it 10? No, it's going to be both of those, 60 times A. So A is equal to 48 divided by 60. And that's equal to 0.80 meters per second squared. So then we can put that into V is equal to V naught plus a T, where we know our V is 4.0 meters per second. V naught is 0 plus 0.80 meters per second squared times our T that we're looking for. So then we're going to have 4.0 divided by 0.80 is equal to T, and then that works out to be 5.0 seconds. That's how long it would take. All right, 17. What is the net force on a 5 kilogram cannonball going from rest to 150 meters per second in 0.50 seconds? So if we're needing F net, that's MA, so we need to get the A because we have what the net force is. So mass is equal to 5.0 kilograms. V naught, well, it's at rest, so that's equal to 0 meters per second. Our V final is 150 meters per second. That's pretty fast. Our time is equal to 0.050 seconds. And so we need our acceleration. So we'll be using V is equal to V naught plus AT. And we'll have 150 is equal to 0 plus A times our 0.050 seconds. So that's going to be 150 divided by 0.050 seconds equals A. And that acceleration, sorry, just finding the question, that's equal to 3,000 meters per second squared. That's a pretty good acceleration. If we come back up here, we use now our 5 kilograms times our 3,000 meters per second squared. That's then equal to 15,000 newtons. That's how much force was exerted on the cannonball. All right, what is the final velocity? Question number 18. What is the final velocity for a 150 kilogram motorbike and a 50 kilogram rider? Notice that they're giving these two masses separately, but again, you're going to just have to add them together. And they're going from rest to when an 800 Newton force acts for 11 seconds. All right, so they're sort of mixing up the values. You can sort of see that what are all the different things that we can ask? How can we pull out one of those questions and plug in something new? All right, so let's write down. So V is what we're looking for. V naught traveling from rest is 0. Our mass is going to be 150 plus 50. I can do that in my head. 200 kilograms. We have a net force of 800 newtons. And our time, that's equal to 11.0 seconds. We need to know our A. So to calculate the A, we're going to use our kinetic. No, are we use? No. We're going to use our Fnet to calculate our A. Is equal to MA. We have 800 newtons. Our total mass is 200 kilograms times our A. And so our A comes out to be 4.0 meters per second squared. And so then we can use V is equal to V naught plus AT. So V is equal to 0 plus our acceleration, which is 4.0 meters per second squared, times our 11 seconds. And so that comes out to be 44 meters per second, not squared, just 44 meters per second. And there we go. All right, 2 more left. A 0.5 kilogram, they talk about a model rocket, goes from 20 meters per second to 45 meters per second in 0.70 seconds. What is our F net? Well, our F net is equal to our mass times our acceleration. So we know what the mass is. What we don't have is the acceleration. So we're going to have to use V naught is equal to 20 meters per second. Our V is equal to 45 meters per second. Our time is equal to 0.70 seconds, and we need to do our acceleration. So V is equal to V naught plus AT. Our final velocity is 45 is equal to 20 meters per second plus A times our 0.70. What? She said workout pause. Oh. All right. So as my wife just came in and said hi. So we're going to have 45 minus 20 is equal to 0.70a. 45 minus 20 is equal to 25, divided by then our 0.70, that's equal to a, and that's equal to 35.7 meters per second squared. So our F net is equal to ma, so that's equal to 0.50 kilograms times our 35.7 meters per second squared, and that's then equal to 17.8 newtons. There's the net force. We're just at 30 minutes. We're just about done, and hopefully you've been fast forwarding as you need to. All right, question number 20. A 2 kilogram sponge drops from rest, so B naught is equal to 0. An air friction force is equal to 5.0 newtons acts upon it. How fast will it be going after 6.0 seconds? All right, so what we need to do is we need to find an acceleration. And we also have to understand what our F net would be, because we can get F net is equal to ma, and we can come up with then our acceleration. Well, our F net, because here's our sponge, well, what forces do we have acting on it? Well, we have our force of gravity, and we have our force of the air. Oh, okay. So now we need a force of gravity, which is 2 kilogram sponge. So if we have our force of gravity minus our force plus a negative force up is equal to ma. Force of gravity, which is 2 times our 19.6 plus a negative 5 newtons is equal to 2.0 kilograms times A. Not 19.6, I'm getting ahead of myself, 9.8. This is going to be 19.6 minus 5, so that's going to be equal to 14.6. It's equal to 2.0 times A. So A is equal to 14.6 divided by 2, that's 7.3 meters per second squared. Now, we have an object falling through air, force of gravity, and the air friction going up. If you calculate an acceleration that was greater than 9.8, it's not going to happen. Because on Earth, the fastest that things can accelerate due to gravity is equal to 9.8. And so here, it's always going to be less. All right. So there we have our acceleration. And so then what we can do is use our kinematics. So B is equal to B naught plus AT. B is equal to 0 plus our 7.3 meters per second squared times our time, which was 6 seconds. And so then our V is equal to 43.8 meters per second. And I believe that was, yeah, they said 44. So there we go. Yeah, good enough. All right, ladies and gentlemen, enjoy your weekend. All right, take care.